Okay, welcome back to EE210B. Let's continue our discussions on inference strategies over networks. So the material for this lecture is based on chapter 12 from the text that you have, which again you can download from our website. Now, if you remember what we did in the last few lectures, we spent several lectures on establishing that the networks are stable, right, in the mean sense, in the mean square error sense, and in the fourth moment error sense. And then I spent 2 lectures deriving performance expressions for these networks, right? We ended up with an expression for the mean square deviation, MSD, and for the excess risk, ER, for the network. And these expressions depended on several parameters. They depended on the Hessian matrices, they depended on the noise, gradient noise covariance matrices, and on the entries of the Perron eigenvector, right? Very good. So now we know how to study the performance of these different networks. So let's now look at these performance expressions and see what they tell us about the network, right? How do we compare networks to each other? If I give you 2 different topologies connecting a certain number of agents, which one would converge faster? Which one would give you better MSD? Or does it make a difference? Does the topology make a difference, right? Can I make networks match the performance of centralized solutions? Okay. How do I design the combination weights? How do I select the combination weights? Questions of that sort. That's what we are going to see today, okay, in this lecture. So here I'm reminding you, right? I'm reminding you of the definitions. So H sub k is the Hessian matrix at agent k at the Pareto solution, right? And G sub k is the gradient noise matrix, right? Remember that because we are dealing with the general complex case, we extend the gradient noise vector, right? SKE, where you put the SK and the SK star transpose, right? It's a 2m/1 vector. And this is the covariance matrix of it, the one below here in the complex case. And in the real case, it's just RS, right? Which is the expected value of SS star. Right, the RQ is the expected value of SS transpose, if you remember, right? So this is just to remind you of what these parameters are, okay? And this is the performance expression we derived last time, right? So here you have the MSD, and you have a similar expression for the excess risk. This is the MSD over a distributed network, whether you are using consensus or diffusion strategies. This is the performance to first order in mu, or mu max, where mu max is the maximum step size. It depends on G's, on H's, and on the Q's. And remember that the Q's are related to the P's, right? And to the step sizes, okay? And from this expression, you observe also that the performance is equalized across the agents. All of them will have this performance to first order in mu. Differences start appearing in second order factors, okay? But to first order in mu, all of them will look similar, and that's the expression, okay? And this is the performance of the network. If you average across the network, that's what you get, okay? Very good. And then I showed you an example last time. I said, let's consider a mean square error network where each agent has a quadratic cost. In this particular case, the Hessian matrix will be block diagonal, RU transpose. So I'm assuming uniform step sizes, uniform covariance matrices in this example. And the covariance matrix in this case for the gradient noise will have this form. I don't care about the off-diagonal elements because once you multiply H inverse by G and take the trace, the off-diagonal elements do not matter. Remember, I did this example last time. And then if your matrix happens to be doubly stochastic, then the Perron entries will be 1 over n. N is the number of nodes. And we derive this expression. Remember, I'm just reminding you of the example. This is the performance of your network. No matter how large your network is, the performance will be given by the average value of the noise power across the network divided by 1 over n. Multiplied by mu m over 2, and that's exactly the expression we derived earlier in this class for the centralized solution. So for mean square error networks, the distributed solution can match the centralized solution. And in the next few slides, you're going to see that this conclusion actually is more general. It's not only applicable to quadratic costs, to more general costs. I will establish the same result for general costs, J sub k, right? That satisfies the usual conditions that we have, right? Convexity and so forth, okay? But another thing I mentioned last time is, even though the distributed solution can match the centralized solution, and therefore is better than the non-cooperative solution, right? If you have n agents running independently of each other, what would be the average performance of the non-cooperative solution? You would just have 1 over n, one of them, right? The other will not be there, correct? You already know that, right? Yes?
Yeah, now you say that the distributed case, the performance is the same as the centralized. And how about the rates? How about the...
Yeah, you asked the same question last time, and the rate of convergence is the same, right? You saw, I showed you the expressions, okay? So, so here you see that the distributed solution, right, will be better than the average solution over the non-cooperative network, right? But what about the individual agents? Each individual non-cooperative agent will perform according to mu m over 2 times the corresponding sigma v, right? Is it always true that this average that you get here, scaled further by 1 over n, is always better than each individual performance? We saw before that this is not the case. The same thing will hold here, right? So for example, okay, let's take an example here. I have 2 agents only. The noise power at one is sigma v squared. The noise power at the other is 5 sigma v squared. So the average will be 3, and then you further divide by n, that gives you 1.5, right? So the performance in the distributed network will be proportional to 1.5. The proportional, I mean, because you have the mu m over 2, right? The performance at node 1 will be proportional to sigma v squared, which is better. At node 2, it will be worse, right? So this is an example where, even though the network performs as well as the centralized solution, better than the average non-cooperative solution, you don't necessarily perform better than each individual agent. You understand it? The same problem we had before with the centralized solution, okay? So that's what I'm saying here, okay? It's not the case that every agent, therefore, will benefit from cooperation. The network as a whole benefits, but not every individual agent. The natural question becomes, like you asked last time, right? Can I pick the A to make sure that I don't only improve over the non-cooperative solution on average as a group, but individually as well, right? And we will see that the answer is yes, we can do that, okay? Very good. Okay, and that's exactly the question that I'm asking here. Can we do better? Okay, so I'm going to answer these questions in the general case, not just for quadratic costs, but for general costs, okay, convex costs. So this is my setup. I'm going to assume the step sizes are uniform across the agents. Why? Because I'm comparing with the non-cooperative case. The performance for each non-cooperative agent is proportional to mu, right? So to normalize, for these comparisons to be meaningful, I don't want the performance to vary just because a node is using a different mu than another node, right? You understand? So let's assume all the nodes are using the same step size, and let's assume also all the nodes are interested in the same solution, right? So that you compare how well all of them are doing in meeting the same objective, right? So that the comparison is meaningful. Okay. Okay, so here it is. So I'm going to assume that all of them are interested in estimating the same omega 0. So let's assume they all have the same minimum, which happens, for example, in the quadratic case. They all have the same step size, and all costs are strongly convex, so that the non-cooperative agents are able to solve the problem and find the minimum. That's all, okay? Very good. So, but now this is not necessarily quadratic. Now, in the previous lectures, we derived these expressions. I'm just listing them for you here, okay? So let's look at them. Look at the second one. What was this? This is the performance of the non-cooperative agent K. If you have agent K running an algorithm, the stochastic gradient algorithm on its own, what performance will it get? Mu over 2. H is just the data type, complex or real, right? H is 1 or H is 2. So forget about H, okay? trace of the Hessian at agent K inverse times the gradient noise at agent K, right? Okay. By the way, this quantity here will come up many times. I'm going to be calling it theta K, and I'm going to put a square just to emphasize that it's a non-negative quantity. Okay, so I call it theta K squared. Fine, so this will be my notation moving forward. Now, the centralized solution, the performance was, I add the Hessian matrices across all costs, inverse times the sum of the G's, and down here you have the corresponding expression for the network. It's very similar. What's the main difference? The main difference is that they appear scaled by the Perron entries, okay? So here I'm assuming this is for the case of consensus or diffusion, right, where the QK is mu times P. Fine? So see the relation? And this is the average performance over the non-cooperative network. So what do I want to do now? Okay? I want to show the following things. These are the results we are going to show. First of all, if the network is, well, you can see it right here, right away, okay? I don't need to go through the proof. Let's assume that my network is using a doubly stochastic A. What will be P? 1 over n. If you put 1 over n here, 1 over n here, how does the first expression compare with the last expression? So it's obvious to see that. Even more generally, distributed solution matches the centralized solution, right? So that conclusion is still there. Okay. Now, in the doubly stochastic case, how does the distributed solution compare with the non-cooperative solution? How does the centralized solution compare with the non-cooperative solution? We proved this before. This was the lemma we proved earlier in an earlier lecture, right? Using some linear algebraic arguments, that this expression 1 here is always less than expression 3. We proved this analytically. Okay, if you go back, you will find this result, okay? And therefore, in the doubly stochastic case, since this becomes the same as 1, the same conclusion will hold here, right? So for doubly stochastic cases, networks, the network will perform as well as the centralized, better than the non-cooperative network, right? And what about on average? But what about at the individual level? Well, you already saw an example. Even in the quadratic case, that's not true, right? So you only need an example to show that this statement is not true, right? So here at the individual level, this is the expression, right? Because when you put 1 over n, at the individual level, it's not necessarily the case that this expression here will always be smaller than this expression. Correct? Okay, you only need one counterexample. I already showed you one for the quadratic case. Okay, of course, there are cases where this will be smaller. For example, let's take an example. Okay, let's take an example where the H's and the G's are uniform across the network. It so happens that H and, okay, so what will you get here? The sum of P is 1. You will get here H inverse. What will you get here? You will get, no, sorry, let's assume doubly stochastic again. Okay, I'm still talking about the doubly stochastic case, okay? Here you will get NG, right? That NG, the N cancels the N that you have here that came from the P's, right? So then the expression becomes the same.
It's N squared.
Sorry, there is N.
There's an N inside H.
So what you have here? Anyway, I have it in a future slide, so we can look at it more carefully here. Okay. Sorry, I already said all of this, okay? That's why I'm skipping it, okay? So I'm now focusing on the individual agent performance. When is this smaller than that, right? In general, it's not. I gave you examples, okay? And in some cases, right? For example, when this is uniform, what do you get here? You will get 1 over n H inverse. What do you get here? Ng, correct? So this cancels that, and you have an additional 1 over n multiplying the trace H inverse G, right? So if the Hessian matrix is a G, and so there are cases where this is This holds even for a doubly stochastic network, right? But not in general. Fine? Okay. Very good. So that's what I'm talking about here, okay? So in that case, the relation will hold. Okay, so this is the example. I already explained it even before getting to the slides. Okay, so that's what happens here, okay? So this is the conclusion, that the performance of the network will match the centralized solution and will be better than the non-cooperative on average, but not individually unless some particular conditions hold, okay? So as a whole, as a group, you will always benefit from working together. This is what this is saying, right? The group will benefit from working together, and you can do as well as the centralized solution to first order mu. Yes?
Shouldn't this be strictly less than?
Yes. Yeah, the lemma was strictly less, right? Yes. Okay. Fine? Okay. Okay, let's continue. Again, I'm just repeating it with more colors, okay? And I think there is a typo. Strictly speaking, it's not wrong, but that's the statement, okay? So I'm giving you an example. This is the metropolis rule. If you remember, if I'm an agent, K, he's my neighbor L, he has a degree, NL, I have a degree, NK. Degree is the number of neighbors you have, right? So the weight I'm going to assign is inversely proportional to the maximum of our degrees. This is called the metropolis rule, okay? Very popular rule. What's nice about it, it's doubly stochastic. You can verify. Columns add up to 1, rows add up to 1, okay? So the Perron entries are 1 over n, right? So if you want to simulate a network with a doubly stochastic A, you can use this, right? Okay. I have an example now. This is what I'm doing here. Okay, I'm running an example. This is the step size. Okay, real data, 20 agents. Okay. I'm running diffusion, adapt, then combine, and I'm comparing with the centralized. I'm just running a simulation to illustrate these ideas, right? So let me go to the curves. There it is. You can see that the diffusion and the centralized are essentially on top of each other, and they match the theoretical expression, okay? Which is interesting to conclude that the network, imagine, this can be a very large network and it can be very sparse, right? Right? You can have, let's say, 10,000 agents, and each agent only has 2 or 3 neighbors, and yet the network is able, in steady state, right? Here, coming back to your question, the convergence rate, right? It cannot be clearer than this, right? Okay, and the steady state behavior. Okay, very good. So you get the point. Now, what if I move to left stochastic policies? Okay. Because in the previous result I showed that on average I will do as well, right? The network as a whole will do as well as the centralized solution, better than the average non-cooperative solution, but not necessarily better at the individual level, okay? Can I come up, okay? Can I choose my A such that I will always do better at the individual level as well, okay? That A has to be left stochastic. It cannot be doubly stochastic because there are counterexamples for doubly stochastic policies where this is not possible, right? Very good. So let me show you that indeed there is a left stochastic A that allows you to achieve that kind of behavior, okay? So I have to tell you what A it is, right? So to solve this problem, this is what I'm going to do, okay? I'm going to solve it in this case because for this case we have a closed form expression for the solution, okay? Not in the general case. So I'm going to solve it for the case where the Hessian matrix is uniform across the agents. For quadratic costs, this is very reasonable because this is usually the case. The RU is the same across the agents, okay? In machine learning, in pattern recognition applications, you have the different agents are interested in minimizing the same risk function, and the Hessian matrix ends up being the same. So this is not an uncommon situation, okay? Now, when the Hessian matrix is the same across the agents, okay, here I'm repeating the expressions, okay? The performance for the non-cooperative agent will be the trace of H inverse GK. G can still be different, okay? For the network, what will be the individual performance? Here you will end up having H inverse times sum of p's. Sum of p's is 1, right? So the sum of p disappears from here, and that H inverse I can put it here, correct? Okay, so the performance becomes the trace of the sum of p squared H inverse G. Here you have trace of H inverse G, correct? Okay. So now I would like to formulate the following optimization problem. This is my problem. This is the performance at a single every single agent, right? This sum. Okay. Of course, I removed the scaling factor. It doesn't matter, right? Okay. So now I'm asking myself this question. I'm given the topology. I would like to pick an A. I would like to pick what coefficients, weights to put on the edges, right? So I would like to pick an A such that those P's that appear here are the Perron entries of the A, right? And I would like to pick the A that minimizes that cost. At least find one such A, okay? You can find others in your homework problems, okay? Let me find an A that solves this problem, okay? You understand what I'm saying? Very good, okay? You see, I can switch, just so that I can bring the trace inside, take the sum outside, right? So this becomes the sum of pk squared trace of this. What did I call that trace? Theta k's, right? So I'm going to write this more simply as the sum of pk squared theta k squared, okay? So my problem, the problem I need to solve, okay, here, I'm reminding you of the definition of theta. So the problem I need to solve is, well, where is it? Minimize over A, left stochastic with these Perron entries, right? The sum of pk squared theta k squared, correct? Given the thetas, solve that problem. Okay. So this is how I'm going to solve the problem. I'm telling you what the answer is. And then I'm going to show you the answer, okay? The proof is not difficult. I will let you check most of it, but this is the answer, okay? The answer is this. I'm given the thetas, trace of H inverse GK. How do you find the thetas? In the next lecture, I'm going to give you algorithms to estimate the thetas, because technically you may know H, because you know the costs, for example. You may know H, or you may not know H. But you need this theta. This theta depends on the trace of H inverse G. It depends on the gradient noise covariance and on H. You may not know these quantities explicitly, so you need to estimate them. But let's assume for now that I know this theta, okay? If I know the theta, this is the A. You construct it as follows. You see it has a very similar structure to Metropolis, except that you add these thetas as weights, okay? If you think of theta, what is theta? Think of it again. Theta is defined as the trace of H inverse G. This is like the inverse of signal to noise ratio almost, because G is noise. H, you can like RU is signal. This is like noise over signal, or one, right? Like one. So theta is like 1 over an SNR measure. That's an interpretation for theta. It's related to signal to noise ratio, okay? So what this is saying, this is the solution, and we call this matrix the Hastings matrix, okay? Because it appears in other contexts in papers by Hastings and others, okay? And these are the degrees, okay? And this particular matrix has these as Perron entries you can show. This is a theorem, it requires proof, right? This is one solution to the problem. Which problem? Okay, the problem I'm solving is this problem. Okay, I would like to minimize, so how, okay, I want to solve the problem of minimizing the sum of p squared theta squared over A, subject to the fact that A is left stochastic, P is its Perron entries, right? But the way I'm going to solve this problem, I'm going to forget the condition that A is left stochastic. I want to simplify the problem. I want to solve a simpler problem. I just want to solve this problem here. I want to solve, find those P's that minimize the thetas are given, subject to the condition that the p's add up to 1. Okay? And then I'm going to show you that the solution that you get, of course, they will be positive, and they will lead to an A that's left stochastic, and I'm going to find p's for you, right? The p's that I find, they will be positive, they will add up to 1, okay? And I'm going to construct an A such that this P is the eigenvector, the Perron eigenvector for that A, and that A is left stochastic. Then I would have found an A. All I want is to find an A, right? But rather than solve the original problem, which is difficult to solve, I'm going to solve a simpler problem and show you, by the way, this solution satisfies the condition. So this is just an indirect way of solving the problem. Okay? How do you solve a problem like this? For example, Lagrange multipliers, because this is just quadratic here, you see. Collect the p's into a vector, collect the theta squared into a diagonal matrix, right? Introduce the Lagrange multiplier. Just solve this problem. You get exactly that the p's, each pk, just p, is 1 over the corresponding theta, normalized by the sum of all the thetas. Each pk is 1 over theta, so it's an SNR, right? Like 1 over theta is like an SNR, normalized by the sum of all of the thetas. That's the solution that you get to this problem. Okay, this is what I showed here. Yes.
Why are you including the Laplacian the other conditions?
I'm not including it. Okay, I'm saying I'm not. That's why. Okay. Okay, I'm going to use these conditions and show you that what I get satisfies the other conditions, and therefore I have a solution. I have one solution, right? That's how I'm solving the problem, okay? So that's why I did this here, okay? So, you see the P that I got here, these are positive P's, right? So they satisfy that condition. And then what I'm saying, construct this A. What is this A? On the off-diagonal elements, right, you put these ratios, and then you complete the diagonal elements so that they add up to 1. Okay? Very good. So now, I claim the only thing that remains to show is that this A is left stochastic, and that this A times the P's is P again, correct? Okay. Checking that this is left stochastic is very easy. You just do the algebra. That the rows add up to 1 or the columns add up to 1 is not difficult, okay? Sorry? Left, the columns add up to 1, okay? So to show that A times P is P, again, this is just algebra, okay? I'll show it to you quickly. And then that completes the argument. To show it to you quickly, right, this is what I need to show. Right? Each column times the corresponding p's. So here it is, you see. I'm making k go from, right, 1 to n. So I want to show that this linear combination is p, correct? This is what I want to show, that A, P is P, correct? So you take a row here. Okay, so let's say the Lth row, you see here the Lth row, you change the column index. I want to show that that's P. Okay, if I show it, then I'm done. Fine? Because checking left stochastic is simple, I'm not doing it. If I show this, then I'm done. I prove the theorem. Okay? So this is how I show it. First, let me show you the symmetry relation, which is, okay, which is useful. So let's take ALK multiplied by PK, which is exactly what you have here, correct? Take these two scalars. I gave you the expression for A, I gave you the expression for P, correct? This theta cancels this theta. Well, I can replace it by theta L. Nothing changes, correct? Now this becomes AKL, because I switched, you see K became L. And this becomes PL, right? So this symmetry relation holds. If you switch, you see L to KK, if you switch K to LL, this relation holds. Fine? Simple to check. Because of this, now I can prove that it is left stochastic. How? Let's consider this sum now. Okay? Consider this sum. What is that sum? So I'm I removed the diagonal element, AAL, PL, and kept the rest, correct? For the rest, I switched the indices. And then I put them together, right? Put them back together. I switched, I put them back together, this with that, correct? Well, but now this sum is over K, so this PL here can go out. And because it is left stochastic, you get PL, right? Okay, so the algebra is not difficult, but there it is, okay? So the interesting thing here is that I found an A that minimizes the MSD, right? This is 1/8. We refer to it as the Hastings rule, okay? Now this A will turn out to have some useful properties. So since this minimizes the MSD, of course, the MSD that you will get, if I take now those P's and plug back into the MSD expression, I will get the smallest possible MSD I can get for that network, correct? No, I'm getting there, right? You did not let me finish my statement, okay? If I take those P's and plug them into the MSD, I will get the optimal MSD I can achieve. Will it be better or worse than the doubly stochastic MSD? Because this is at least, right? Because this is the best you can do. Okay, so it will be better than the centralized, right? Okay, of course, this may look puzzling at this moment, right? How can it be better than the centralized? Okay. Yeah, exactly. So there is an issue which I'm going to explain later, but forget this point for now. It will definitely be better than the non-cooperative, but what about at the individual level? It will turn out that at the individual level it will also be better. Each one of them will individually be better, always. Okay, so let's prove it, right? Okay, so here it is. Okay. Another aspect that I still need to show is that this A0 that I constructed is primitive. Okay, because if you remember, all the MSD expressions I derived in the previous lectures were under the assumption that the network is strongly connected, which means that A has to be primitive, which means one of the diagonal elements of A has to be positive. That's all. If you can show that at least one case positive, actually all of them will be positive. I do the algebra here. I will not do it. Just write down what the algebra is. Okay, and it is here. Okay, so the way I'm doing it, just so that you see, this is the expression for ALK, right? This is definitely smaller than the numerator. I keep it unchanged. The denominator, this could be the maximum or the smaller value. So obviously this is always smaller than that, which is smaller than this. Okay, so this property holds. Okay, if this holds, then if you add all the A's, okay, on a particular row, except for the diagonal one, okay, so this will be upper bounded by that, right? You are adding, okay, 1 over nk, how many times? Nk minus 1 times, because, right? So that sum is nk minus 1 over nk. But if I add akk to it, this sum should have been 1. So akk is 1 minus that, correct? So that's it, 1 minus that. You get something which is positive, right? So actually every diagonal element will be positive, so your matrix is primitive, right? Very good. So I don't have to worry about that. So now the interesting thing, if you take those pKs, optimal pKs that I derived for you, and plug them into the MSD expression, okay, right? Because remember, what was the MSD expression? It was proportional to the sum of theta k squared, pk squared, right? And now each one of these pKs is 1 over theta k squared, the sum of, correct? So you see that this cancels that. Okay, you're going to get something like that, okay? This is the optimal performance. Fine? Okay. The optimal distributed performance. Okay? In the doubly stochastic case, if you go back, you see, in the optimal case, you get the inverse of the average of the inverses of the thetas, right? It's like a harmonic mean, okay? Whereas, if you go back to the expression for a doubly stochastic solution, okay, this is what you get. Fine, just go back to the expression, put the p is equal 1 over n. This is what it is. So here, right, and there is a relation, by the way, that tells you how this relates to that. This inequality, you can prove it. This is an algebraic inequality, okay, a homework problem, okay? For any collection of n numbers, non-negative numbers here, the sum of a's times the sum of 1 over a's, this product is always larger than or equal to n squared. So I can compare this sum to the sum that appears in the previous expression, which involves this, and conclude that that MSD is smaller than this MSD. You understand? Okay? So there it is. So this best MSD, right, is better than the MSD you would get in the doubly stochastic case, right, which is intuitive because we optimized it, right? And obviously better than the non-cooperative solution. So far so good. But what about the individuals, right? The individuals. Well, here it is. What is the performance of each individual agent in the network? This is the expression. It is the same network MSD expression. Well, if I ignore the sum and keep only one of the elements, you see, 1 over theta squared is smaller than the sum. So the inverse is larger than the inverse of the sum. So obviously less than or equal. And this is exactly the performance of the non-cooperative solution, right? Because what is the inverse of 1 over theta? This is simply theta, correct? Which is the trace of H inverse GK, right? So you see, you do get that the Hastings rule ensures that not only the network is performing better than the centralized solution, better than the non-cooperative solution, but also better on an individual basis. You understand? Interesting, right? Okay. Of course, the question is, this is all very nice if I can find what the Hastings rule is. To find the Hastings rule, I need the thetas, right? I need to know trace of H inverse G, okay? And in general, I don't have, for example, in the mean square error case, I don't have the RU, which is the H. I don't have the G, which is sigma V squared RU, right, proportional to that. So knowledge of these quantities require that I know, right, requires that I know the noise power and the regression power, which I don't know. So I have to estimate them. We'll do that next time, okay? But if I could estimate them, I can design a network that will outperform the non-cooperative solution and the centralized solution. Now you might say, how can a distributed solution outperform a centralized solution? Okay, why? The reason why is because you are giving the distributed solution more information. The distributed solution is using the A's, correct, to do the combinations. And those A's are defined in terms of the SNRs. You are telling the distributed solution what the SNRs of the different agents are, essentially, right? And telling them to give more or less weight to information arriving from these agents in accordance to their SNR. The centralized solution is not using any of that information, right? It's just using the data. The new weight is the old weight minus a step size times the sum of all the gradient vectors, right? And these gradient vectors are not being weighted by any information that tells the algorithm give more weight to this gradient vector than this other gradient vector, right? The distributed solution is doing that. That's why it can perform better. You understand where this... So it's not puzzling because of that, okay? Okay, so we established this. Okay, so this statement is stating what we proved. Okay, and this is just an example. Let's go back to an example. Same step size, uniform covariance. Okay, here it is. So remember, the theta is the trace of H inverse G. If you do the calculation, this is the theta. Okay. Now train the algorithm using the Hastings rule under this theta. By the way, sometimes, for example, the Hastings rule involves thetas up and down, correct? Remember that each A had something like this. The maximum of something like this, correct? Right? For example, if the noise variances happen to be the same across the ages, they will cancel out. You don't even need to worry about them. So sometimes, right, the theta cancels out. You don't really need to estimate it. Okay? In that case, if it cancels out, you end up having the metropolis rule, right? You get, so the metropolis rule ends up being an optimal solution, right, in this case. Okay? Okay, so here it is. I'm writing what the A is for this case using the thetas that I showed you. That's all. This is just an example specializing the result to the quadratic case, okay? Very good. You already saw that the distributed solution is better than the non-cooperative solution, and this is the performance, okay? And then you can do this for online learning where you have a single cost. So H is uniform across all agents, and the gradient noise, this is the real case, it's RS, it will be uniform across all agents. So theta will be uniform across all agents. It will cancel from the numerator and the denominator. And what would be the Hastings rule in this case? The metropolis rule. So the optimal rule for learning, for online learning in this case, is the metropolis rule, which happens to be doubly stochastic. So if you run this rule, okay, to solve a learning problem for any risk that you choose, this rule will be such that it will perform, okay, in this particular case, because it's doubly stochastic, it will match the performance of the centralized solution, like we showed earlier in this lecture, but it will perform also individually better than each individual agent, right? Because this is the Hastings rule in this case. Understood? Okay, very simple. Okay. Yes.
Is the Hastings rule the only?
No. There are other solutions to that problem, and in some of your homework problems, I asked you, okay, to check that. Okay. There are other. This is not the only solution. There are others. Okay, but this is a popular one, a famous one, right? So now I already did the comparison with the centralized solution, that the optimal distributed solution performs better. Why? Because right, this average here, okay, you see here you have 1 over n, the sum of the thetas, that's the usual average, okay? And here you have the inverse of the sum of the 1 over theta squares. This is related to a harmonic mean average, okay? And because of the relation between these two sums that I showed you before, the distributed solution will be better than the centralized for the reasons I explained, okay? The question now, can I modify the centralized solution in order to match the performance of the best distributed solution? And the answer is yes, give it this additional information. How, right? So this is what you can do, okay? This is the distributed solution we used before, correct? In this distributed solution, you are giving the same weight 1 over n to each gradient vector, right? If you modify it and weigh the gradient vectors in proportion to this p, remember this is the optimal p that was given as 1 over theta k squared normalized by the sum, right? So this p is proportional to the SNR. So you are giving more weight to better gradient vectors, right? So if you use that p here, right, and derive the MSD for this algorithm, the MSD for this algorithm will match the optimal MSD we derived for the network, okay? You understand? Now, by the way, it's very easy to derive the MSD here without having to go through all the derivations we did before, because you see, if I am to define the gradient noise here, okay, come back here. The gradient noise is the difference between this gradient and the actual gradient, correct? There is 1 over n here, okay. The gradient noise here, I can define it as the difference between you see, put 1 over n times n here, okay? np this hat minus np the true gradient, right? So the gradient noise here is proportional to the gradient noise in the previous case, and the proportionality is n times p, correct? You understand? I can write this as 1 over n times np times this. So the only difference between this and the other is that there is a scalar np multiplying the approximation that I'm using, okay? So the gradient noise here is a scalar times the previous gradient noise. So the covariance matrix here is np squared times the covariance before, correct? Okay? And the Hessian here, because the function is multiplied by np, right, is np times the Hessian before, correct? So all you have to do is go to the MSD expressions that you use for the centralized solution, replace the Hessian by np times what it used to be, replace the gradient noise covariance by np squared of what it used to be, and you get the results. You understand? I'm trying to solve it without having to redo all the calculations, right? So here, you see, it is as if I have scaled the costs by np, okay? This is the original gradient noise. This is the new gradient noise. Okay, so you see that the new Hessian matrix and the new gradient noise, okay, they are scaled accordingly. So just go to the expressions. If you carry out these scalings, okay, you will find out that the new MSD, right, because the new theta is np times the old theta, and the new p here, we know what it is, you will find out that the expression will match. You understand? So if you scale your weighted solution in a similar manner, you can recover the best distributed solution, right? So that was not an anomaly, it's just because you are not giving enough information to the centralized solution, correct? So you see, once you have these expressions, you can answer questions like this. You can now play with the network, right? Design your A, compare how different networks perform, right? Okay. And then I have a simulation here just to show you that this is indeed possible. Okay, so this is the step size. Okay, uniform H, this is G, this is theta. What I'm doing here, I'm running now 3 algorithms. Diffusion, using the optimal A's. So this will be the best network you can get in this case. The usual centralized solution, and the weighted centralized solution with the optimal weight. So what do you expect to see? The learning curves of this and diffusion to be almost on top of each other, and this to be worse, right? And the simulations confirm the theory, okay? So this is what you are going to see here. This is the network. This is the noise power, and RU is uniform across the agents. And if you plot the learning curves, this is what you see. Okay, you can see that the red curve is the regular centralized, the black curve here is diffusion, and the one a little bit below it is the centralized solution, okay? You see, and it matches the theoretical expression we derived, okay? So you can recover that performance if you normalize the entries of the centralized solution accordingly. You understand this point now? Convergence rate is the same, okay? So now you can repeat all of this for the excess risk, okay? So I'm going to rush through this part because you will be bored, okay? And I will be bored, so, okay? But I'm showing it to you here so that you know, just like we have results for the MSD, we have the same results for the excess risk. So let me go through this quickly. In this case, I'm assuming all the agents are interested in minimizing the same risk function, okay? These are the expressions, just like for the MSD we had before. Again, when you have doubly stochastic, this will match the centralized, okay? Will be better than the average, okay? But not necessarily better than the individual. Same issues, okay? Okay. Same issues, okay? Again, not necessarily better, and I give an example here of 2 agents with, okay? not necessarily better. So then I formulate the same problem. Let's find the A that minimizes the ER. The solution turns out again to be the Hastings rule. The only difference here between this and the MSD is that theta now is defined differently. Theta now is simply the trace of R, because this is the real case. There is no G, there is only RS, and H doesn't appear. You see, if you go to the ER expressions, you don't see H inverse. Right? That's the difference. H doesn't appear. So theta is different, that's all. Okay, but everything else, the mathematical formulation is the same. Okay? Here, you will get the same solution, Hastings rule, and then you will be able to show that the optimal is better than the distributed solution and better at the individual level. Okay? And then here I have an example to show that. Okay? Comparing distributed and centralized learners, uniform step size. Okay? I run diffusion. This is logistic diffusion, okay? So the agents are solving a logistic regression problem. And here I'm running a centralized, weighted centralized solution in this case, okay? In this case, the Hastings rule in the learning problem is the metropolis rule. So it's doubly stochastic. So the scaling will just involve, okay? Anyway, if you run these are the expressions we derived. Okay, let me just show you the simulation. This is the simulation. Okay, you can see that, of course, it's a little bit better, the centralized solution. Okay, these differences here are due to the approximations we do in the analysis. Okay, but if you use a smaller step size, because the theory says they are the same to first order mu, so mu has to be very small. So if you reduce mu further, of course, these curves will get closer and closer. Okay. But the point is that they both are going to the theoretical results we derived, right? So the excess risk part of this lecture is very similar to the MSD part. Fine? Okay? Very good. So today, okay, what I did today was to use the MSD or ER expressions from last time and try to design now the combination policy optimally. Let me pick the A that gives me the best MSD or the best ER, and I gave you one solution, the Hastings rule. And I showed you if you use that solution, the whole group will benefit as a group and also individually, right? And we established that analytically by comparing the expressions, okay? So in the next lecture, we are going to use these expressions a little bit more and get a little bit more insight into other aspects related to the behavior of the network. Okay, some surprising effects come up that you are going to see in the next lecture. Okay, so I'm going to take a break for 1 minute and then we move to the next lecture. Okay, so good. I know you were happy, so okay. Okay, welcome back to EE210B. We are going to continue our discussions of inference over networks. So last time we optimized the choice of the combination policy over the network, and we showed how you can make the network perform as best as it can, even in comparison to the centralized solution, and also at the individual level when you compare individual agents in the network to individual non-cooperative agents, right? And this was made possible because now you have performance expressions. You can massage them, you can manipulate them, and try to extract as much information as you can, right? So that's the kind of analysis you can do. So today I'm going to show you further properties that come out from these same performance expressions, okay? So what I'm going to do, I'm going to study the following problem. The problem where I have networks with a mixture of informed agents and non-informed agents, or uninformed agents. I'm going to define that. You see this type of behavior very often in biological networks. For example, if you remember in my very first lecture, I showed you simulations, right? Let's say you have a school of fish moving in a certain direction and suddenly they turn back, right? They turn back suddenly because one or two fish took that turn, right? They saw something, right, that frightened them, right? So those had information that the others did not have. And that particular behavior influenced the entire network, right? So that's one example where you see problems like this, where you see problems where some agents may have more information or may have the information while others do not, right? So how does it affect the behavior of the network to have more or less informed agents? What do you think? If I have more and more informed agents, let's say I start with a network where 10 agents are informed, 20 are uninformed, and then I move to a state where 20 of them become informed and 10 are uninformed, which situation do you think is better for the learning behavior of the network?
The ratio matters.
What did you say?
It's the ratio that matters.
Okay. You did not answer the question. Okay. Anyway, so let's see. It's not always the case that having more informed agents help you improve the solution. It's not. Okay, and you're going to see that. Okay. So let's look at that. Okay. So this is based on chapter 13. Right? There is even a saying that says too many cooks spoil the broth or something like that. It applies here. Right? This is the mathematical proof for that. Okay.
But they proved it for beehive networks.
Sorry?
They proved it for beehive networks.
Yeah. So the analysis here, right, is going to show you, at least shed some light on this kind of behavior. Okay. Of course, in the context of networks, I'm not talking about bees, but I'm giving you examples, right, where you see this kind of behavior in biological networks. Okay, so this is based on chapter 13 from my notes. Okay, so here I'm just introducing the topic that it's not always the case that all agents will have access to information, and I give you examples here. You see, of bees and fish, where often only a small fraction of them tend to be informed, and the others are following around, right? Okay, very good. So let's study this case where I have a network that's trying to solve a learning problem, an adaptation problem, an optimization problem, but not everyone is informed. So I have to define to you what I mean by informed. Okay, so let's define that. Okay. So when you are running, each agent is running a distributed strategy, right? Let's say diffusion, just to keep it simple, right? Diffusion. What do you have to do in diffusion? Let's say ATC. You adapt, then combine, right? So if I'm agent K and I want to do adaptation, okay? So so here I'm defining informed agents and uninformed agents. An informed agent is one that can do both steps, adaptation and combination. To do the adaptation, you need gradient information, right? You need to be able to compute an approximation for the gradient vector. You need to have D and U, for example, in the mean square error network, right? If you don't have that, you don't have a gradient, you cannot perform the adaptation step. But you can still talk to your neighbors. You can still do the consultation, the combination step, right? So informed agents can do both steps because they receive information and they can talk to neighbors. Uninformed agents will be ones that do not receive information. They can only do consultation. So they help in spreading the information, but not in modifying it directly. Okay. So this is the mathematical definition. Okay. So an informed agent, again, I have the H there, you can remove it and just focus on the real case or complex case, just to keep it general, right? Okay, so an informed agent will be able to do something like this, right? It is running an adaptation step, which is the first line, followed by a combination step, which is the second line. Every informed agent in the network is doing that, and I'm going to assume all of them are using a uniform step size mu. Okay, of course, positive. Now, and so this is informed, okay? It receives data and therefore it can do that. Now, the uninformed agent does not have the gradient information, right? So it cannot perform the adaptation. It doesn't receive D and U, for example, in the quadratic case, right? In the learning problem, also it may not have the gradient information, okay? So it's as if it has 0 here, right? So all it can do is send its W to the other agents, right? This is what I know so far, okay? And average the size it receives from the other agents. So its W is changing actually, right? Because it is still interacting with the neighbors. I'm not getting information, but let me see what you have, improve my estimate. And then, right? So in a sense, they help relay information across the network, right? And that's in the fish example I showed you, right? When these two turn around, and then the entire school ends up turning around, that information propagated to the network, right? Somebody propagated it. You're seeing the example here, okay? So now, very good. So ultimately, because actually this phi in this case is W, right? So okay, anyway, so this is what's happening at the uninformed, okay, agents, okay? Now, so the difference between informed and uninformed for me is whether they have mu0 or mu non-zero. If they switch, so think of this mu as having 2 states, on and off. If it is on, it's a constant mu. If it's off, it is 0. If an agent turns its mu on, then it becomes informed, right? Okay, very good. This is the model I'm using. Of course, you can come up with more or less sophisticated models, right? But this is the model I'm using in this study, right? Okay. And again, I'm going to focus on consensus and diffusion, which means you set 2 of the A's to the identity matrix, the third A to some combination matrix. Okay, just to keep the discussion here focused rather than very general. Okay, what conditions I need? Well, when all the agents are informed, we used to solve this problem, right? The network was solving that problem, okay? But now, if some agents are uninformed, so let me first introduce my notation, okay? I have n agents in total. N sub I informed agents. So the I is to say, right, a subset of them is informed. Okay, so the set of informed agents is calligraphic Ni, okay? This is the set of all agents for which mu is positive. So this is the set of informed agents. Now, if some agents are uninformed, the network will never see any information about the gradient vector of that cost, right? So the agent cannot be minimizing this sum, because it will never, for example, if node 1 is uninformed, right, and then the network is running the algorithm, nowhere you are going to sense J1 or its gradient vector, right? Okay, so when you have informed and uninformed agents, what you are actually doing, what your network is doing, you are minimizing this effective cost, which is the sum of the J's over the informed agents. That's what's happening, okay? Because the network is only using the gradient information from these agents, okay? From these agents, okay? Very good. Of course, if the JKs happen to have the same minimum, then the minimum of the effective cost and the minimum of the global cost are the same, correct? It doesn't really matter, right? But if the individual costs happen to have different minima, then this problem will converge to its Pareto solution. The other problem will converge to another Pareto solution, right? because you are minimizing this cost, and its Pareto solution will be different from the other Pareto solution. You understand what I'm saying? Okay. So the first remark I wanted to say is because some agents are uninformed, you are not receiving information about these J's. The network is only seeing those J's. Okay? So this is the problem, the effective problem that the network is minimizing. Okay? The sum over the informed agents. Okay?
Why would an uninformed agent why would it even possess a cost function? What does
No. It can have a cost function, but that cost function doesn't mean anything. It's not using it anyway, right? The network as a whole, it's as if that cost function does not exist, right? It's as if it is a zero, right? Think of it. This is the sum over n where some of these costs are zero, right? Because it doesn't exist, okay? Okay. So all I'm trying to say is that the solution that you converge to, W star or WO, depends on this set of informed agents, right? If all of them have the same WO, then this is the same WO as the global cost, okay? So it's actually independent of an I, okay? But more generally, it will be a W star, okay, W star, I think I write it on the next page. Okay, so I'm coming there. So what conditions you are going to impose on this cost? The same conditions we usually impose on the global cost that we are trying to optimize, that it is strongly convex and therefore uniformly bounded from below, and that its Hessian matrix is bounded from above, right? This corresponds to a Lipschitz condition on the gradient vector, right? We always impose conditions like this. Since the network is minimizing this effective cost, so we impose the conditions on the effective cost, right? That's all, okay? Very good. Okay, so this is a typo here, okay, just to say, okay. So now I'm solving this problem, the problem you have here, the one in red, okay. Very good. Just like happened in the case when the individual costs do not have the same minimum, where will your network converge to? To a Pareto solution. What was that Pareto solution? It was the unique minimum, right, of a modified cost. Remember? How did we modify that cost? We modified that cost by multiplying the costs by QKs, right? It's mu k, pk over the informed agents, because the other J's you can think of them as being zero. They are not there. You understand? Okay. So this is the W star is the minimum of this. If the costs happen to have different minima, the Pareto solution will be determined by the minimizer of this cost, right? Okay. Very good. And these P's, they are the Perron entries of A, correct? So far I'm just formulating the problem, right? Nothing changed. The only thing that changed is that everything that's happening is determined by these informed agents so far, okay? Now, of course, I made a statement here that the algorithm is going to converge to the Pareto solution of this, and I motivated it, right? I gave you the intuition, but technically you have to prove it, right? So I'm not repeating the proof, I'm just telling you that if you repeat the proofs of the previous lectures or previous chapters, these are the steps that are going to change, but the conclusions still hold because of this, because of this, because of that, right? That's what I do in this chapter. So for example, okay, so here I'm telling you that the Pareto solution depends on the set of informed agents, which makes sense, okay? And that you can still show that you are going to converge this close to that solution, okay? By repeating arguments we did in the previous lectures. When you try to repeat these arguments, okay, what will change when you try to repeat these arguments? What will change, for example, if you remember, there was a 1D11 matrix that kept appearing in our arguments. It will now be defined as a sum only over the informed agents, not over all agents. We needed this matrix to be positive definite. It will continue to be positive definite. Okay? Why? Because we are now assuming that the effective cost is strongly convex, right? So this condition will still hold. Okay? So that's what I'm saying. So if you go back to the argument, you will see that the conditions that you needed there will continue to hold if we assume that the effective global cost satisfies the conditions that we usually assume that the original global cost satisfies. You understand? That's all. Okay, so the arguments can be repeated to conclude that actually the Pareto solution is the solution to this. If you want to identify it, this is how you will find it, okay? Fine so far? So everything so far is intuitive, makes sense, okay? And what about the performance expressions, okay? So this is, I'm just repeating another place, okay, where what you need, this sum will be over the informed agents, but it will continue to be positive, definite, so the conclusions we derived will continue to hold, okay? Very good. What about the performance expressions? Okay? Remember that for a network where everybody is informed, this was the performance expression, right? I know you know it by heart by now, right? You have seen this so many times, right? Okay. What will change? What will be the performance over a network with where a subset of the agents are informed and the others are non-informed? Can you guess what will change? The sums will be only over the informed agents. That's what will change. Okay? If you go back to the argument and carry it out, this is what will change. Okay? And what will change with the convergence rate? The same thing. The sum over the informed agents. Okay? So I have the expression. I'm stating these facts because I'm saying if you go back to these expressions and do what you need to do, you'll arrive at these conclusions that you have here. You see? Sum over informed agents, sum over informed agents, sum over informed agents. Fine? Very good. So now that we have performance expressions for these types of networks, let's see what kind of behavior they will show. They will exhibit, right? You have a question?
No,
You seem to have a question.
No, I want to see where it is that we're going to find out that too many cooks spoil the book.
Okay. At this stage, you are uninformed. Okay? And I am informed. Okay? So very soon the information will get to you. Okay? Okay. So look at the first expression. Okay? Look at the first expression. Assume now I add more informed agents. Okay? If I add more informed agents, okay, of course, adding in the sense that those three are informed and then I added one to them. I did not change the previous ones. Okay, so let's add, okay. Okay, because those are the P's of the informed agents, okay? If I add one more agent that's informed, remember, those P's are positive, right? And the H's are non-negative, okay? So what will happen to this sum if I add one more positive agent? It will become more positive, right? It will become more positive. In general, it will become more positive, but not less, right? Okay? So the smallest eigenvalue of that matrix will only go up. And you're of course, mu is very small, and you're subtracting from 1. So what happens to alpha? Becomes smaller. Okay, so you will converge faster, right? So if you have more informed agents, you will always converge faster. Not necessarily a better solution, right? Okay? Try to solve an exam problem with 20 people giving you hints on how to solve it, right? Okay? You will converge fast to some conclusion, but not necessarily the correct conclusion. So far, you know that it converges faster. But what about the MSD? If I add more informed agents, what will happen? What will happen here? You are adding because there is something positive. What will happen here? You are adding, but this is inverted, right? So unless the algebra is such that this combination decreases, right? You may go up, you may stay where you are, right? So this is the term that determines it. So I'm going to show you examples now, analytical examples, where depending on the topology and on the combination policy you are using, right, adding more informed agents can make things worse or better. Yes.
Saying there is only one informed agent.
Yes.
Why isn't this similar to the case of non-cooperative case?
One. Okay. So what does that mean?
If I have one informed,
No, it will be similar. Why not similar?
We'll have PK.
Sorry.
We'll have PK compared to the non-cooperative.
No. But in that case, no. But remember, you still have.
I mean, what's the contribution of the non-informed agent here?
The non-informed agent is relaying information around, right? The non-informed agent is relaying information around, right? Okay. Now, Okay, let's do some examples here, okay? Now, continue. Okay, so this is what I was saying. So if I enlarge the set of informed agents, alpha will decrease. You saw that, okay? So this is the kind of behavior I'm going to show you. On the left, okay, so the informed agents are in the light color, okay? Blue color is uninformed, okay? So when you go from left to right, you are adding more informed agents, okay? So we already know that the convergence rate, the alpha, is becoming smaller, right? But you are going to see that the MSD doesn't necessarily become smaller, it can go up, okay? So let's look at this. Okay, let's look at an example, okay? Here, let's look at an example. Okay, I have several examples. I can just do one in detail and then you get the point, okay? And then the others are just repetition. Let's do this example, okay? Okay, so I have uniform step sizes, uniform covariances, right? This is the complex case. So this is H, this is G, okay? And all of them have the same minimum. Fine. So this is a network, a mean square error network, where everybody is trying to solve the same problem. Okay? So if you write down what the convergence coefficient is and what the MSD is, these are the expressions, fine? Over the set of informed agents. Now the alpha, we already know what's happening with alpha, so let's focus on the MSD, okay? On the MSD. Now, if I add one more, let's just say I added one more agent. So this sum that you have here will be the previous sum plus this new P, correct? And this sum here will be the previous sum plus the new P times the new sigma. I'm adding a new agent, I'm making it informed, okay? So the new MSD will be better than the old MSD if it is smaller. So this is now a simple algebraic question. If I add a new P and a new sigma, when will the new expression be smaller than the previous expression, right? You can find conditions on the new P and the new sigma. Just simple algebra, right? Okay? Okay, so here I'm first studying the case when everything is stochastic, okay? So I'm going very slowly. So let's take the case when everything is doubly stochastic. So P is 1 over N. So P disappeared, okay? So I have a doubly stochastic network. Okay, so it's just a matter of adding a new sigma or not. So now I'm asking this question. If I add a new sigma, what will change? This changes, becomes Ni plus 1. And this sum becomes the previous sum plus the new sigma. Now you ask the question, and this is just scaling, you can ignore it, right? When is this new sum smaller than the previous sum? Right? Simple algebra, right? If you do this simple algebra, in this case, in the doubly stochastic, here, you see this is the new sum, correct? This is the old sum. If you do this simple algebra, this is the conclusion. If the agent that you're adding, this is for the quadratic case, right, mean squared. If the noise, its noise, is larger than the average noise across the already informed agents, it will make your performance worse. Right? That's the conclusion in this simple example. In this example, it is intuitive. In the other examples, it will be less intuitive. You understand? In this case, everything is doubly stochastic. Mean square error, uniform step size, uniform RU. If I'm going to turn him on, right, I have here informed agents, I'm going to add one more. His noise level, if it is less than the average, it's good. If it's larger than the average, it will worsen the performance, right? Intuitive conclusion. Here it is. So the analysis tells you that. And then the simulations will confirm this, okay? So in this simple example, that's what you get. Let's do another example. You understand? Makes sense. Okay, good. Let's do the other example. This is the case where I am using the averaging rule. This is very popular in the social sciences, right? If I have 5 people giving me information, I simply give you weights that are, I have 5 neighbors, 1 over 5 to each one, right? 1 over 5. 1 over the number of neighbors, right? Uniform rule. Each one of us weighs the neighbors inversely to the number of neighbors, right? This is the uniform rule. Now, this uniform rule is not doubly stochastic. You can check. The uniform rule is left stochastic. And we have a closed form expression for its P. Do you know it? Pk is nk normalized by the sum of the nks. That's it. Okay. Essentially, you know, P, by now you should know, this Perron entry is a reflection of how important you are in the network, right? The P, because the P appears in all these performance expressions, it reflects, okay, so here, in this network, the more connections you have, right, because it's nk over the average, right, the more relevant you are in this network, right? Very good. So now, if you write down, here it is, right? This is just some algebra, you can prove this, okay? So, if you write down, for the alpha I don't need to do calculations because we already saw in the general case what the pattern is, so, okay? I just wrote down what the MSD is by replacing the expression for the P's, okay? Fine? You believe me that this is the okay? This is what you get. Okay. Now, if I add a new agent, what will change? This sum will be the old plus nk prime. This sum will be nk prime squared, sigma vk prime squared, plus the old, right? Now you ask yourself the question, how should these factors be chosen such that the new MSD is worse or less, right? Or better than the previous? Just do the algebra. If you do the algebra in this case, okay, here it is, okay? You want this to be larger than that. I mean, to be worse, right? So if you do the algebra in this case, this is what you get, okay? This is what you get. Okay, so let's, okay. You see, if the new node that you are adding, if its weighted variance is larger than what you have on the right-hand side, I'm going to explain this on the next slide, okay? What do you have on the right-hand side? Similar weighted variance. So now the variances are weighted by how many neighbors you have. This is a weighted variance, right? A weighted variance divided by the sum of the degrees across all informed agents, right? Okay? So now it is not just his noise variance, but a weighted version of it, okay? So how many connections the person brings and how much noise the person brings matters now, okay? This is the condition. If you are adding an agent that satisfies this, then you will be worse, right? Okay? Now, you see in the first example, when your A was doubly stochastic, the conclusion was very simple. If you add an agent whose noise power is larger than the average noise power, it will do worse. Here, you can rewrite this in a nice way also where if you add an agent whose power is larger than the harmonic mean, not the arithmetic mean, the harmonic mean, in this particular case for uniform rule, that's what will happen, okay? So for example, define these variables xk. What are these variables? They are the inverse of the noise weighted by the degree, right? Okay. And let's introduce the harmonic mean of these variables, okay? So here it is, okay? So this is the harmonic mean. Okay, this is the weighted harmonic mean, okay? The weighted harmonic mean, okay? The regular, if I have variables, you see, let me define it here. If I have variables measurements xk, n of them, what is the arithmetic mean? 1 over n, the average of xk, correct? So what is the harmonic mean? Okay, the harmonic mean, okay, you average the inverse and then the inverse of that. Right? Right? So what you have here is something similar because this is weighted. Okay? This is the weighted by these n's. Okay, the weighted version. Over there, each 1 over xk is weighted by 1. Weighted by 1. All of them are weighted similarly by 1. And you added all these ones, that's why you got the n there, capital N. Here they are weighted by nk. You add all of them, you get the n, okay? So this is a weighted harmonic mean. So what the previous conclusion says, this is the value of the variable x that you're adding. If the x prime that you're adding is smaller than the harmonic mean, okay, then the performance will get worse in this case, okay? If the new x that I'm adding, the new agent that I'm adding, has x value smaller than the existing harmonic mean, it will do worse, right? So this is non-trivial in this case. It's less trivial than the previous case, right? You wouldn't have thought of this, right? It's not, okay, the previous one maybe you could have guessed. If it's bringing more noise than what I have, I will do worse. Here it's not that trivial, right? This weighted and weighted, correct? Fine. Okay, here I have a numerical example, okay? So the code generates this colored network, okay? So it took me some time to do this, but this is automatically generated and randomly, okay? So what you have on the left, you just tell it on average how many informed and informed agents you have, okay? So what you have on the left, so uninformed is red, no information. Yellow has some information, informed, right? Okay, and they are trying to solve an estimation problem. In this case, I think it's a mean square error network. On the right, what I'm going to do, some of the uninformed, I'm going to make them informed. So 13 over there became green, okay? And 19 over there became green. The other uninformed, right? So the analysis I did is for the case where you keep the previous informed, you add to them, right? You don't just change everything randomly, then these results will not hold like that, right? Okay, you understand what I'm saying?
So the switching is stochastic? Or
No, I'm switching some of the uninformed nodes, but keeping the other informed. If you start switching, some of the red ones become green and some of the yellow ones become red, then these conclusions I'm talking about, they do not hold. You have to figure out what will happen, right? Okay, if I ask you in a homework problem and then an exam problem, turn on 6 and turn off 12, what happens, right? Now that's a different kind of question. These conclusions do not hold, right? Okay, you understand here? So I'm simulating this case, okay? And did I say what kind of combination policy I'm using here? Let me see. Do I say that?
first line averaging.
Okay, so I'm using the averaging rule. So this is the case about the harmonic mean conclusion, okay? Anyway, this is the noise power across the agents. So some have more noise than others. This is the signal power, okay? And this is what you have here, okay? So in this particular case, I added 2 more informed agents. So the convergence rate will become faster. So that's the red curve there. Okay, but these 2 agents that I added, if you check the conditions, they will be such that the performance worsens. Okay, you can see, right? So it's very consistent with the theory. Okay, and you can see that the expressions are very close to what the theory predicts, where you are going, right? So this is an example where adding informed agents is not necessarily beneficial. It can be, of course. I'm not saying it cannot be. But you can see it's not always the case that it is beneficial, right? You may have that impression, but interesting enough, that's not the case because of the coupling between agents, okay? Okay. Now, another interesting thing, you might say, okay, I expected you to ask this question, right? Okay, so
Because it converged faster, that's why
right, okay. So what I'm seeing here because the convergence rates are not matched, right? Because when we often try to compare algorithms, we try to fix one of these parameters and compare the other. We fix their convergence rates and compare the MSD, or we fix the MSD level they are tending to and compare their convergence rates. And this way the comparison is more fair. So in the next example, I'm going to fix the convergence rate and see what happens in steady state, okay? So now, how do I fix the convergence rate? If you go back to this expression here, okay, this is the convergence rate, okay, for this example, for the uniform rule, okay? On top, you have the sum of the degrees of the informed agents. In the bottom, you have the sum of the degrees of all the agents. Now, to fix the convergence rate, whether I am in this state or in that state, I need to make this convergence rate independent of the number of informed agents. correct? So I'm going to choose the mu, okay? So I'm going to choose the mu to be dependent, essentially, to be inversely proportional to this number, such that regardless of whether I am in this state or in that state, the convergence rate is the same, right? Okay, and then let's compare for that mu, what would be the MSD, right? In this case and in that case. You understand what I'm doing? So this is what I'm doing in the second experiment, right? So here it is. I'm going to pick the step size to be proportional to the inverse of that sum in the numerator, right? Still, mu 0 is very small, so I can control the smallness of mu through mu 0, right? Okay, but I scale it by this number. This way, the alpha now becomes independent of the number of independent agents, right? So if you look there, now this alpha is independent. For both networks, the convergence rate will be the same, correct? Now, if I take this mu and plug it into the MSD expressions, right? Here it is. Okay, this is the MSD expression that you will get. Okay, I just see now you have mu 0. Okay, now in one state I have a collection of informed agents. In another state I will add one or two more informed agents. So let's add one more informed agent. Okay, assume I add one more informed agent. So this doesn't change. This part doesn't change. This part changes. This part changes, correct? And now I ask the question, what condition this new agent should have for the new MSD to be worse than this MSD? If you do that algebra, you get this expression. Fine? Okay? It doesn't look as nice as before, so this is non-trivial, right? Non-trivial, okay? So if the degree of the new agent is large enough, this is what this is saying. If it is larger than a certain, if it's large enough, okay, if that person is too well connected, that can degrade your performance, okay? Brings in too much noise, too much information, right? Okay, now, okay, so it will get worse if this happens, okay? Now, of course, this is the condition, but is this a practical condition? Do I have networks that satisfy a condition like this? So in the next slide, I show you examples where this can be satisfied. These are networks where these conditions are satisfied. Okay? So even though the convergence rate is the same, the MSD will be worse. Okay? Okay. So this is, I give two examples. Maybe it's enough to discuss only one. Okay? So let's discuss. Okay, so now verify that there exist situations. Okay, so let's consider first one, the following case. Let's assume all the agents first have the same degree. You happen to have a network where all agents have the same degree. Fine? This is a typo in the notes. I forgot the 1 over ni here, okay? Okay, so then the condition that you had before, which looked complicated like this, right? If you just make now all these nks the same, this condition simplifies to this. If I'm adding an agent such that its noise power is not only larger than the average power that I had before, but sufficiently larger, at least twice as large, that will make it worse, right? Okay, that's one case, okay? When all the ends are the same, okay? The second example, let's assume that the noise power is the same. In one case, I assume the degree is the same. Let's assume the noise power is the same across all agents. Then if you go back to the expression, you will see that the condition now is this, okay? You have now a condition on the degree, right? In the previous case, the condition transforms into a condition on the noise. This one transforms into a condition on the degree. If your degree is large enough, then your performance will also get worse. Understand? So you see, all these results, you just get them by manipulating the expressions that you now have, right? You can ask all kinds of questions now and answer them, right? So the way you should look at this is just as examples illustrating what you can do now that you know the expressions, right? Okay? And anyway, so I didn't show a simulation, but if you simulate it, you will see the convergence rate is the same. But if you simulate networks under these conditions, the performance will get worse. Okay? Fine? Okay. So what was the conclusion of this part? Okay, the conclusion was it's not necessarily the case that if I add new informed agents, the performance will improve, correct? Okay, you can do the same thing for the ER, by the way. I did it for the MSD. You can also have similar conclusions for the excess risk. Okay, I have them in the notes. I may have some slides on that, but I don't need to go through it. It's very similar. But now, the second question that comes up, okay, can I design the A in such a way that I always gain by having more informed agents? Right? It's a useful question. Okay? In other words, let me control how you want to contribute, fine, but let me control how you're going to do that. Right? I know that you have bad SNR or good SNR, so I'm going to give this much weight to your input and this, right? So guess what the answer would be here? What A should you use? The same Hastings rule we derived last lecture will work here. If you use that rule, look what will happen. Okay? Again, let me show you an example. Remember, we derived the Hastings rule under this condition, right? Uniform Hessian matrix, okay? It would be interesting to solve the same problem for H that changes across the agents. It's much more challenging, okay? But that's, okay, a useful problem. So, uniform step sizes, uniform Hessian matrices, okay? And remember, I told you what the optimal A is, right? In terms of the thetas, each theta was the trace of H inverse GK, correct? And that A has these P's, fine? So if you use the Hastings rule, that rule will have these P's as Perron entries, correct? I'm just reminding you what this theta is, correct? The inverse SNR measure, right? The type of inverse SNR measure. Now, go back to the MSD expression, okay, that you have for a network with NI informed agents. That expression depends on the P's, correct? Plug into that expression those P's. What will happen? You understand what I'm saying, right? The same expression of the alpha we already know, okay? What happened in the alpha, okay. Anyway, for both alpha and MSD, let's plug these P's, right? Okay, so if you do that calculation, this is what you get. For the MSD, the expression becomes now independent of the number of independent agents. So now whether I add more, right, or not, the performance will not change. Okay? If you are using the Hastings rule, right? If you are using this rule, okay? And what about the convergence rate? Well, the convergence rate still has this expression here, okay? Which depends on the sum of the 1 over theta squared over the informed agents. You understand? So you can't control the degradation in performance, okay? You can't control the degradation in performance here. Make it flat. Okay? And then the last part of this lecture is just to tell you that similar conclusions hold for the ER. So I'm going to go quickly through this, just so that, okay? So remember, this is the expression for the excess risk. Okay, depends on P, RS, because this is the real case, there is no H, correct? Okay? Then again, we have informed agents, uninformed agents. Okay, this is an example what the expression will be if I have informed agents and sub I of them, right? And now you can ask yourself the same question. If I add, okay, so which A I'm using here? Well, this is a general A, right? If I add a new agent, what will happen? You are increasing here, correct? But that's an inverse, and you are increasing here. So again, right, you have a condition, okay? So you can figure out what that condition is. So if the new agent that you are adding, okay, if the new agent that you are adding satisfies this condition, it will worsen the ER performance, correct? These expressions, by the way, are also useful in the following manner. If you want to add an informed agent, you can check if there is anyone that will help you and turn it on, right? Or you can check if some is making your performance worse than it should be, you can turn it off. These expressions, you can use them also for that purpose, right? Okay, so this is very similar. Okay, and this is another example where I have a doubly stochastic metropolis rule. Okay, in this particular case, the metropolis rule is actually the Hastings rule. The Hastings rule, okay, that's why you can see that the performance in this case is independent of the number of informed agents. Okay. Okay. If you instead use the uniform rule, right? Then we know what the P's are. Then you can ask the question, if I want to add a new agent, what should be the degree of that agent for the performance to get better? So nk prime should be less than that. If it is larger, it will be worse, right? Okay, so that's what you can do with this type of analysis, okay? You get the point? So what I wanted to show you in this lecture is another example, right, of what you can do with the performance expressions we derived before. And to show you this interesting behavior, that it's not necessarily the case that adding more agents helps solve your problem better. You will converge faster, but you may be converging faster to a bad situation or to a worse situation, right? But there is a way to control the degradation in performance if you happen to know the Hastings rule, if you happen to be able to know the thetas to construct the Hastings rule, right? So next time I'll show you one way to estimate those thetas. It would be an adaptive way. And therefore, by estimating the thetas, you are implicitly estimating the A's. So you end up now with a two-layer adaptive algorithm, one for, let's say, diffusion, adaptation, and combination, in parallel with one for adapting the A's that diffusion is using. You understand? Okay?
Professor,
Yes.
we look at it from a different perspective, starting with all agents being informed.
Yes.
Like what we had.
Yes, yes.
And then saying, let me remove some agents
Yes.
to improve the performance.
Yes.
Can we do that?
Yeah, you can do that. Now you can ask the question in reverse, right? So rather than going from ni, you go to ni minus 1, right? So you can ask the question in reverse. And I think I have some homework problems where I ask you questions like this. If you were to pick one to improve the performance the most or to degrade the performance the most, which one would you pick? Something like that, okay? So you can answer, okay? So what I'm trying to say, once you have these expressions, you can work with them and you can answer questions like this, right? Fine?
Professor, how
Yes.
about the case where you start with few informed agents and then automatically the other agents become informed? You don't control them whether to add them or not.
Right. So what this analysis is showing, if they automatically decide to turn on or off, that's fine. But the performance will change accordingly to these expressions, right? If they happen to be ones that satisfy this condition or not, the performance may go this way or that way, right? All this analysis is trying to show you is that it does matter who the informed agents are, where they are, and it tells you exactly how to find that, how to quantify that, right? You have the tools to do that now, okay? So I'm going to stop here today, okay? Thank you.